let's continue. Yeah.
The question for design, why not doing this update the words negative K and with just the agent who encourage you to do things quickly. It's considered the time.
So what do you mean by negative? Where?
Because when we change the scenario, we just decrease the reward by the lapse time. The agent just get the rewards as quick as possible. Because in this way, I think it's not always obvious that you take optimal.
Well, okay, the question is, instead of doing plus k times square root of 3, do something like minus k times 1 over square root of 3.
To minimize the errors.
So then that is not an optimistic reward anymore, right? Like, so you're reducing, you're taking away rewards for settings which you have not seen before. So it might have some unexpected effects in the dynamics. I'm not sure that is same. I don't think it is exactly same as what this is achieving. Yeah.
Just I did remember like this in dynamic, you just suggested replacing that ST and RT, or we are just keeping them with tau and adding.
Okay, we are keeping them adding new stuff. I think so, yeah.
We are now replacing if the state and action appears again.
Just give me 1 second. Sorry, can you repeat?
Replacing the same state and action appears again.
Oh, then you will update the tau.
Yeah, here we are only updating the tau and keeping the new state. Like if the ST and AT comes again, then we will.
Okay. Well, you could replace. You could replace. So, well, so this boost that you're seeing is because it is deterministic case and there's no replacement, right? Like, so for every state in action is only one next state, right? So but it is true that like when you have stochastic settings like this might not be. But this is a very simple improvement to
that. So it's like with the stochasticity, it is already working, but replacing part, but the replacing part also hurts that the older tau that I was having. It's a new information.
Yeah, that's right. Okay, so now this is fine. Yeah. Do we still need to do exploration? That's a good question. So this is already an exploration method, right? Like, so probably you don't need to do epsilon. Well, you might still need to do epsilon greedy because like this is only to explore the other regions, like but to explore little things near your policy, like it doesn't hurt to do explore epsilon greedy. Okay, so this is fine. So now let's talk about some of the practical like implications and like improvements that one could do with this dynamic framework. Okay, so the first thing that we're going to talk about is the idea of prioritized sweeping. Okay, now what do I mean by prioritized sweeping? So now if you think about why the n is equal to 50 model was doing much better than n is equal to 0 model, right? Like, so now in any of these classical versions of the algorithms, like things like policy iteration or value iteration, like, so we will go through all the states and update their values, right? Like, so for all the states, like especially in tabular setting, right? Now, do we really need to go through all the states and make updates? Okay, so now if you think about the example that we have seen, like with just one episode, like what can you learn, right? So even if you go through all the states and make an update with tabular mode structure learning, most of these updates are going to be useless, right? On the other hand, we know what is useful, right? Like in that particular example, maybe let me go back to that example. So I have to move slow so that screen is not on. Okay, so here you can see that what is most important to update is this particular state, right? Now, once the state, like the value for this state changed, then we know what is next important, like what is next. In the next iteration, even if I go through all these states, okay, I'm not going to make a lot of changes. Like the only change that I would make is for this particular state, right? Similarly, in the next iteration, the only change I'm going to make is for this. Well, of course, all these things together. So then this thing, like all these things together, right? Like, so in some sense, like if we can do some sort of working backwards and do updates only for these states that come in our back, right? So that is going to be computationally much more efficient than actually doing an entire suite of updates, right? Now, this is the idea behind prioritized sweeping, okay? But of course, this intuition that I gave you was with the notion of goal state. I know what was the goal state, I reached the goal state, so then I go backward, right? So let's just call this as backward focusing computation. Okay. However, we need something much more general, right? Like what if there is no goal state, or what if you haven't discovered the goal state yet, right? Like, so now you might get rewards on the way, right? So this is a very simple ritual where I told you, you get a +1 only whenever there is a goal, right? Like, so what if you get a lot of rewards in between? Like, so now how do we update? Like, so we can generalize this. Like, so like we can generalize this and say that, oh, whenever there's a change, I can just look back and update things nearby, right? Now I can actually start using a priority queue. Okay, that's a good question. So we will talk about it. There are many ways to define the change, right? So like, but the general idea, let's talk about what is the change, like in a moment. Like, but for now, let's say that there's a way to detect changes, and we know that whenever things change locally, like states near that or in the transition are going to be most affected. So I should give high priority for those updates. Okay. So let's say I have a grid world. I don't want to go back all the way. So let's say I have a grid world like this, and there is a change that happened here. Okay. Now I should give high priority to update these states than, for example, these states. Okay. So we're going to do that by using a priority queue. Now this priority queue, I'm going to put states one after another with the priority value. Now every time I want to make an update, I'm going to make an update by taking the top elements from the top states from the priority queue. Is that clear? Now, how do I decide the priority value? It depends on the change. So how do I define the change? So here is one simple way to define the change. Like, so like whenever like you have, let's say, high TD error for a state, okay, then probably like you have to revisit the state often. And you also have to revisit the states next to that often. Okay, so here is a simple algorithm, like so, which we're going to call as prioritized sweeping for, well, in this case, deterministic environment. Okay, so stochastic setting, it's going to become difficult. So the idea is really simple. So you start with an empty priority queue. Okay, now you are in a current state, you take an action by using the policy. Okay, and you put it in the model. Okay, now you compute the priority value, which is basically this difference, okay, in the queue values. Okay, if this priority is greater than some threshold, then I'm going to put that in my priority queue. Is that clear? Now, we're going to do the model learning, like learning. Sorry, this is model learning. So we're going to do the planning part. Okay, this is how I'm going to do it. Like so, I will first take the first element of the priority queue. Okay, and I will learn from that. Then I will consider all the states and actions that led to my current state. Okay, and I'm going to put them in my queue now. Is that clear? Like I considered what are all the previous states for the state, because now they are going to be affected. So I'm going to put them to the priority queue.
Looking direction also in the table?
Yes. We are going to make a lot of updates for sure. So the thing is, previously we were also making a lot of updates, but in an uninformed manner. Like for example, like if you think about how we are doing updates in DynaQ, we randomly sampled things, uniformly randomly sampled a state and we made the update, right? So now we are not doing uniform sampling anymore. We are doing a prioritized sampling. Is that clear?
But the threshold is the time is going to.
Oh, that's a hyperparameter. Let's say. Yeah, you could unleash the threshold. Yeah. Okay. So now this is going to be useful as the number of states increases. Okay. So here is a comparison of prioritized sweeping versus vanilla DynaQ. Okay. Now the x-axis is actually the number of states. Okay. So each point in the x-axis is a different grid world. So like I keep increasing the number of grids in my grid world. Okay. And we are checking how many steps does it take to reach the optimal solution. Now you can see that prioritized sweeping almost always does better than like vanilla uniform update. Is that clear? Any questions so far? Yeah. Okay, that is a good question, but I have to go back without affecting the camera. This one, right? Well, you see the DynaQ is actually slightly better than DynaQ plus is actually slightly better than DynaQ even from the beginning, right? There is a small gap. So the problem with DynaQ is it found a policy, then it doesn't explore much. Okay, so that is why it is continuing with the same cumulative reward. Okay, so however, DynaQ plus explores a lot. So after some point, okay, exactly here, it figured out that there is a better option. So its slopes increases. Is that clear? Okay, so let's go back slowly. Okay, so any questions about prioritized sweeping? Okay, so well, the idea here is if you think about DynaQ, right? So DynaQ was very similar to this algorithm, except for the fact that this particular line, right? So here we are taking the first entry of a priority queue. Instead, we were uniformly sampling something from the model, like from the table, right? Like so this just shows you like how efficient it is to consider which states to update instead of uniformly sampling. Like so here we are going to give priorities to states for which we expect maximum change. So if you go back to that 50 n is equal to 50 example, like when you have one step queue learning, you have only one state which has been affected. So probably the predecessor of that state is the only thing where you're going to have big change. For rest of the previous states, the change is 0, right? So now priority queue, like this prioritized sweeping will tell you, oh, you don't update any of those previous states. You only update this state. Is it clear? Now, if you do prioritize sweeping, you can imagine you do prioritize sweeping for n is equal to 50. You will be updating just that part iteratively, like until you reach the start, right? Like so. On the other hand, like simple DynaQ is not that smart. Is it clear? Okay, so this is good. So far we discussed about how to plan, like how to use model like for planning while learning the policy itself, right? Like so we were looking at the first class of model-based methods. Okay, so now let's actually try to spend the rest of the time on the second class of approach, which is planning at decision time. Okay, now what do I mean by planning at decision time? So in this case, like so far whatever you are doing, right? Like so we are going to call that as background planning. Okay, so what we are doing now is decision time planning. So background planning methods basically work only during the training time. Like so, like once you learn a policy, then decision making basically involves given the state, use the policy, find the next action. Okay. On the other hand, decision time planning is where the planning gets activated at decision time. Okay. When you are taking the action, let's say you are in the current state, you want to take an action. Now, instead of just using the policy, can I actually look ahead and plan what would be the optimal course of actions and take the best possible option? Is that clear? That is decision time planning. Okay. Now, for decision time planning, so we are going to talk about both the discrete case and continuous case, discrete actions and continuous actions. Okay, because the methodology or the procedure for doing decision time planning is going to be a little bit different for both discrete action and continuous action. So far, we focus just on discrete actions, right? Like so, however, like there is not a big difference between discrete or continuous action in background planning, because you take an algorithm, like let's say you take ActionCritic, which can handle both discrete and continuous actions, then you can do planning with ActionCritic, and that becomes Dyna ActionCritic, right? So it is easy to do continuous and discrete actions in background planning. Okay, so however, for deterministic planning, there is a discrete option, there is a continuous option. The discrete option is some sort of search over a tree. Okay, so in the discrete case, you'll consider given the current state. Okay, so 1 second. Okay, so given the current state, right? So we will consider what are all the possible actions. Let's say there are 2 actions here. Okay, now for each action, there are many possible next states. Just for simplicity, let's say there are 2 states possible. We're going to consider only 2 actions, two possible next states, just to make the tree look pretty. So you have 2 possible actions, possible next states, possible actions, and so on. Similarly, something like this, right? So you take, in this case, this is in some sense search based method. Okay, so where we start at some point and try to look ahead, like, so what are all the possible options, right? Like, so we will go through all these possible options, right? Like, so this is one possible option, this is another possible option, this is another possible option, and so on, right? So we will consider all the options and pick the one which has the best possible return. Okay, now to do this, what are all the things you need? So I'm in a current state. If I have to look ahead like this for many states, let's say even till the end of the episode, so what components do I need to do this plan? So given the state, I want to know the possible next actions. You need a policy, right? So in this case, we are doing decision time planning. So we already have a policy that we have learned. Okay, so you need a policy. But we have the policy. So given the policy, you will move from here to here. Right? Now, given the state and action, I need a mechanism to know all possible next states and the reward. That comes from the model. Right? So again, similar to the first class of algorithms, this model might be given to you, or you might have already learned the model offline, or you will be learning the model simultaneously. Okay, so there are many scenarios possible. But in general, to do this search, you need the policy and the model. So if you have access to both, then you can kind of try to look ahead and have an estimate of what happens. Yeah.
So in this case, the sample weight model is right? You need like all possible states.
Okay, that is a good.
You need like something kind of some sort of giving you a distribution.
Yes, so that's a good point. So now, okay, so we are going to fix that. Okay, so that's a good observation. So the observation is like in this case, like I would need I would need a kind of a distribution model of the world, because I want to know all possible next states and action, right? So it's kind of true. Now, there are a lot of options here, okay? Like first of all, like for example, let's say we are interested in games like chess or Go or tic-tac-toe. So let's say you're playing these kind of games where the rules of the world are well known. Okay, in that case, given a state and action, okay, here's the thing. You don't need the probability distribution of the next states. you only need to know what are all the possible next states, okay? So which is often possible with things like chess. Like in chess, you take an action, like you know where you're going to go, right? Like so, the only uncertain thing in the chess is like given a state, there are many possible actions. You consider all the possible actions, then the next state is deterministic. So you don't need to even need or worry about a model of chess, right? Like because in the game of chess, you know the rules. Like so, if you take an action, there's only one possible next state, right? Like so, so in that sense, it is going to be easier. Now, there's also another version of this kind of like tree-based, oh, in some sense, like there is a Monte Carlo approximation to this. Okay, so like so which is what we're going to discuss next, which is the idea of rollout algorithms. Okay, now let us say you just have access to sample models. Okay, one possible decision time planner is this. Like so, I start with the state. Let's say there are 4 possible actions, or let's say 5 possible actions. Okay. Now, I'm going to consider this particular state action first. Okay. And do imaginary rollouts by using my sample model. Okay. So I will do one rollout like this. So for people who don't remember or forgot our graphical notations, like circles are states, dots are actions. Okay, so let's say this terminates here and you get a reward or return, right? So now I will do another rollout. I will do another rollout. Okay, now for each of these states, action pair, I can do many rollouts and use these rollouts to get a better estimate of the actions, like value of the actions, and pick the action which has the maximum value. Is that clear? Now, there is a big difference between, even though it looks like Monte Carlo, there's a big difference between Monte Carlo methods that we have seen so far and this Monte Carlo algorithm. Okay, so the difference is in this Monte Carlo algorithm, like so, you have a policy already. Okay, but you might have a policy or you might not have a policy. Okay, so even if you don't have any policy, you just consider all the states. You estimate the values of these states by doing a lot of simulations, and then you throw away all these things. Next time when you're in a new state, you're going to do these estimations again. Is that clear? So there's no, sometimes there is no learning happening like that is happening in the MC methods that we have seen before. Okay, so in this case, you don't need access to a policy, but you can just start on the state, consider all the next states, you do a bunch of simulations. Okay, now depending on your budget, like so for example, I give you a budget. There's budget of time and budget of space, right? Like compute, right? Like so, if I give you 10 seconds, but I tell you can use thousands of GPUs. Now the advantage of this algorithm, this is extremely parallel. I can in parallel try 1,000 rollouts for all these actions just in 1 second if I have access to thousands of GPUs. Okay, this is the kind of thing that like DeepMind did with AlphaGo. Like so, they scaled up for every move that AlphaGo took. Like there were thousands of GPUs in the back doing these calculations. Okay, so now you can do this in parallel, and if time is the constraint, you can go for parallelism. If time is not a constraint, you can use smaller amount of compute, but for longer time and pick the best action. So is the idea of rollout clear? Any questions?
Just on,
Yeah.
if we are using only the states and the next states, they all just at current stage?
Well, we are talking about one-step models, right? Like, so given a state and action, the model is giving you the next state and the next reward. Now, in the case of rollout, sorry, I think I did a mistake by saying you don't need policy. You need a policy here, okay? So when you are in this particular state, you want to know which action to take, right? So maybe just for this part, you are considering all possible actions. But for the rest, it is a sample, right? So you need someone to tell you how to go from here to here. So for that, you need a policy. So we are going to call that policy as rollout policy. Now, this could be the same policy that you are learning already, or it could be just a random policy, which is not very useful, but it could be any policy, really. Is that clear? Any question? Yeah.
So in the Monte Carlo, you were doing this kind of rollouts, and then you are updating the states, all the states that you visited, but here you are not updating any values. You just take a look at the final rewards at this time and take that.
And then you forget about it and go to the next step. Okay, so now this is where this gets interesting, right? Like, so now imagine you are also learning this rollout policy. It could be using Monte Carlo, or it could be using TD, whatever, right? So now, what is rollout trying to achieve here, right? Like, so what rollout is trying to achieve is to take the rollout policy and always try to find an improvement over the rollout policy. Okay, so had I used my rollout policy also for this particular state, then I would just get the return that the rollout policy can achieve, the maximum return that it can achieve, right? Instead of doing that, I'm doing these extra computation. So with the hope that the return that I'm going to get is strictly greater than the return that I would achieve with my current best known policy. So in some sense, you're doing policy improvement by doing rollout. Is that clear? Any question? Yeah.
Like sometimes heard it that where they say, so for example, you have initially you have learned an optimal policy, and then you are doing rollouts, and by chance your rollouts are bad, and then you end up picking the wrong action.
Possible. I'm not sure about the chances of that. Like, how good is the chance for that, right? Like, because you are following the rollout. Even in your rollouts, you are following the policy. You are not exploring, right? So
there is stochasticity, right?
Oh, yeah, stochasticity could affect things. Yeah, that's for sure. Okay.
You're questioning your own learned policy again.
Yeah, that's true. Yeah. Okay, so well, given the limited time, I really want to do continuous part. So let's try to finish the discrete part soon. So, like, one last thing about discrete part, like, so there are a lot of smart ways to do this search over the state space. Okay, now this gets really hard as the branching factor becomes larger. Like, so for example, like you take games like Go, like what are the future possibilities given the current state and given the current state, right? Like, so that grows so much. Like there are just too many possibilities. Okay, when you have a huge branching factor, the simple tree-based method, like or Monte Carlo, would not be sufficient within the limited amount of time that you have. Okay, so in those kind of situations, like the most default search algorithm people use is what is known as Monte Carlo tree search. Or MCTS. Okay, so this is also the algorithm behind the success of AlphaGo, like, but not the one that I'm going to explain today, but more complex version of this, which also includes learned value networks and all those things. Okay, so but we are going to see a very simplest possible Monte Carlo tree search. Okay, so the idea here is really simple. Like, so we are going to have two types of policies. Okay, so here's the thing. We do rollout with rollout policy, right? But how to cover this huge tree, like so, which has a lot, which has a lot of branching factors, right? Like so, within the limited time, that is not possible. Which means you also now you also need another policy, which tells you how are you moving, like within the tree. Okay, so we're going to have two types of policies: tree policy and rollout policy. So clear? Now, in the case of MCTS, there are 4 operations repeated continuously. Okay, so the first operation is the operation of selection. Okay, now what do I mean by that? Let's probably start with the current state. I just have the current state. Okay, now in the current state, let us say there are 4 possible actions. Okay, I will ask my tree policy, which action should I take? Okay, we haven't discussed what is a tree policy. Let's do that later. I will ask my tree policy, what action should I take? Okay, so my tree policy, let's say it tells me this action is what I should take. Right? Now, once I take this action, okay, I'm going to go to some state, right? So let's say this is the state. Now what I have done is I have expanded my tree. Okay, initially my tree had only one state. Now I took an action, I reached another state. Now I'm adding this to my tree. Is that clear? Now in the third stage, I'm going to do simulations. Okay, so what do I mean by that? So I'm going to do rollout here until I reach the end of the episode. Okay, so I'm going to do many rollouts from this particular state. Okay, now in the final stage, I'm going to do backup, which means I'm going to back up the value to that action. Is that clear? So what have I done here? So now let's see how this works, maybe with another example. Okay, no, yeah. So here you see that in this particular example, right? So like your tree policy, like I have this tree given to me. Okay, now my tree policy tells me how to move in the tree. Okay, so given the root of the tree, my tree policy will tell, okay, you should go here, you should go here, you should go here, you should go here, okay, and you should go here. Okay, so the moment you reach the leaf, my expansion step will add the state corresponding to the action. Okay, now there are many possible actions here, so you can do rollouts for that. Once you finish the rollout, you're going to back up the value all the way up. Is that clear? So in the next iteration, I will again ask my tree policy, where should I go? My tree policy is going to tell me, let's say, for example, go here, here, here. Which means I'm going to do my exploration or search in this particular leaf. So I will consider the next state for potential actions, do a rollout, and back up all the way up. Okay. So in some sense, like what we are doing is we started with just one state. We are intelligently expanding the tree. Okay. I'm saying it is intelligently expanding because, well, we haven't seen what is the reason behind that, because like we haven't discussed what is the tree policy, right? So now this tree policy is what is going to make this algorithm powerful. Okay, so the tree policy is going to take care of the exploration exploitation dilemma. Now, one standard tree policy that people use is UCP. you can have an UCB algorithm as a tree policy, which is going to count how many times you have traveled through these paths in the tree. Okay, it is going to encourage you to travel unexplored paths which are promising. Okay, so for example, let us say this particular path seems to be promising. Now UCB will tell me, okay, maybe you should go in this path. So then I go there to further explore. After doing a little bit of exploration, I figure out that I get negative returns or not so great returns. Okay, now UCB will adjust itself and tell me, okay, so maybe this particular direction is promising. You search there. Okay, you will repeatedly do these 4 steps again and again until you reach your time limit. Let's say I give you 5 seconds to do Monte Carlo research. So now you will reach 5 seconds and then you're done. So then you will just take the current tree, just based on the current tree's values, you pick the best action. Okay. Now, given that we spent so much time in coming up with this smart tree, right? Like, this is not a random tree. This is actually a smart construction of tree. So let us say I'm going to erase all these things. Okay. So let us say that after doing all these simulations, my algorithm tells me that this is the best action to take. Well, it's actually a bad idea. We have done so much exploration in the first site. So let's say this is the good action to take, the best action to take. Okay. Now, I really take this action in the real environment. I reach here. Okay. Now I don't need to start my MCTS from scratch, because I already know that this is a useful tree, right? I can save computations. I can reuse computations from the tree. Let's say we are playing the game of chess, okay? And it's a timed game, like you get up to 5 seconds to take an action. So for the first 5 seconds, MCTS is going to do a lot of search. The next 5 seconds, you already have a good initialization, so you're going to do even more search based on the good initialization. So you're going to get better and better and like perform really good. So question?
The tree selection, so the tree policy is not just the policy over access. It seems like it's a policy over which nodes to select.
Yes, yes. The tree policy is an exploratory policy for the tree. Rollout policy is your actual policy. Now here's the thing. Well, okay. I think I will not do continuous case now. Like I don't want to do that in 3 minutes or 5 minutes. So we are going to do that next week, okay? So that I can spend more time on MCTS. Okay, so here's the thing. If you have a game which goes for so long, now these rollouts can be computationally costly in the sense, if I give you only 5 seconds, if you have to roll out 1,000 time steps, it's not possible, right? Like so now you can consider approximations, like smarter approximations. Like so, you roll out only for, let's say, 5 steps. If you have a good value network, now this value network can tell you, oh, this state has this much value. Okay, so instead of backing up returns, you can actually back up learned values. Now you can learn this value network in parallel. So this is what AlphaGo, like the Monte Carlo research in Go agents designed by DeepMind was doing. So they had a value network, and you are also simultaneously learning the value network, and this is going to kind of approximate the whole rollout, so that you can do much more rollouts in the same time. Is that clear? So any questions? Okay, there's a question. Do we consider the opponent as part of the environment in chess? Yes. So we will definitely talk about multi-agent reinforcement learning towards the end. Okay, so it's in my list. But for now, we are only talking about single agent setting. So when you have an opponent, the opponent is abstracted out with the environment. So when you take but the moment you start modeling the opponent, you can do a lot of other interesting things. We will spend some time on multi-agent model towards the end of the course. Any other? I don't want to start continuous action case, and we will see. Okay, maybe I'll give this as a thinking exercise. Okay, this is also not in the book, so it's a real exercise. Like, so now it was kind of intuitive to do this for discrete actions, right? Because for discrete actions, you can do tree search because there are 10 possible next actions. You can construct this tree. But in continuous action case, let's say my action is the amount of force that you have to put, or torque, or velocity, or speed. Okay, these are continuous actions. Now, it's not very easy to construct a tree here. Right? There are infinitely many possible actions. It's a continuous space. So these kind of tree search methods, well, I think it could be extended, but it is not clear or intuitive, like for extending to continuous action phase, right? So can we do something else? Like, so what can we do to do this kind of search, but for continuous action? Okay. Don't Google. Like, if you Google, of course, you'll find the answer, but don't Google. Like, it's not in the book as well. So I want you to think about it. Like, so, like, well, how would you do this kind of decision time planning for continuous actions? Okay, so we will discuss about that next week. So, however, I think we have to do a little bit of moving things around next week because we have a guest lecture. So the first two parts of the lecture is going to be on eligibility traces, like by an invited speaker. So we have the last part, which we could probably use for the continuous action case. Okay, so in some sense, like whatever we have seen so far, right? So it covers the fundamentals. So next 4 weeks is going to be like more on advanced topics. Like so whatever we have covered so far is like all the fundamentals that I wanted to teach. Like so in the case of oral, like so I think now we have better categorization. We have model free oral and model based oral. And in model free, again, like you could, well, I think there are at least 2 categorizations, right? Like so, like in both, right? Like so, like let's just say there's one way to classify is model free, model based. The other way to classify is value based or policy based, right? And the other way to classify things is whether you're doing Monte Carlo or TD. Let's just put it this way. It's actually very difficult to put everything in one figure. Okay, so, and we have covered pretty much all these like varieties of algorithms, right? Like so, it will be more useful if you can revise all these things like before the next set of lectures. Like so the next set of lectures are going to be mostly ideas on like how to improve these things further. Like so, for example, we're going to talk about eligibility traces, like which is kind of backward. Like we'll talk about both forward and backward view for like things like in-step learning. Okay, so and then we will talk about some advanced topics, like for example, multi-agent reinforcement learning. Like so, we will talk about hierarchical reinforcement learning. Like so, where like so, how can we like currently we are dealing with low-level actions, right? Like so, like okay, nobody asked me this question today. So all the planning that we saw today was one-step planning. But humans don't do one-step planning. Like so, for example, let's say you want to plan to go to France for vacation. Okay. Now, when you plan, you don't plan that. Okay, I'm going to start walking from here. I go here, take left, go here, take right. I can like go here, like open my app, book Uber, right? So, like we abstract out things. Like so, if you want to go to France, you know that okay, from here I should reach airport. So the first level of planning I have to do is I have to go to airport. Probably I take a couple of transit flights, reach France, right? So now that is my high level action. So then I will start worrying about, okay, how do I go to airport? Maybe I don't want to take my car. So maybe it's a good idea to take Uber, right? So that's my next level of planning. So then I would have to plan about what time and all those things, right? Like so humans definitely don't do one-step planning, right? Like so now how can we design these abstract planning methods, like so where you plan with higher level options, right? Like, so that is hierarchical reinforcement learning. So we will talk about hierarchical reinforcement learning. And we will also talk about offline, like, or batch reinforcement learning, like where you learn everything from a data set instead of learning from interaction. Okay, so it is very, very important in a lot of safety critical applications. Like you don't want to learn with interaction, like, so it might cost lives or money, like, or your robot, right? Like, so how to do offline reinforcement learning is something that you will see for sure. And we will also talk about partial observability. So far we discussed really nice examples, like where you see everything in the world, grid world, or like even the card code example that you're doing in your assignment, right? Like, these are all like what I would call as completely observable, like fully observable environments. Like, so, but majority of real life applications are partially observable. Like, you don't have access to the entire world at the moment, right? So then how do you take actions in those kind of situations? So we will talk about all these interesting next level problems in the next 4 weeks. I think that's end of today's lecture. So I will put the scribble for this week and last week so that it is easier. And I will most probably have the notes for the next few weeks. So because we are going to completely move away from the textbook. So, but of course, like the eligibility traces against lecture, I think the speaker uses slides